So I just started the recording, and I just wanted to go over again. We're just some of Dr. Asadi's PhD students, and we wanted to give some background on the lab and some of the research that we look into, and explain some of the opportunities that are in the lab, and then the current questions that you might have for us as grad students, or if you have any interest in grad school, we can answer any questions. So just a little description of myself before I let Nathan introduce himself. My name's John. I got my bachelor's from material science here at UF, and I'm now pursuing a PhD in the fixed lab for the ECU department. And I had done a co-op with Celis Technologies, and they're a semi-cap manufacturer. So they manufacture semiconductor equipment that makes the chips. But now I just spend my days thinking about printed circuit boards and 3D volumes for X-ray reconstruction. And as you see here, we have our 3D model with all the components that give us lots of trouble for verification and other inspection methods for providing hardware assurance in our lab. But I'll let Nathan get his background and introduce himself.
Yeah, so my name is Nathan. I'm another one of Dr. Asadi's students. I came in just a bit before John. I got my bachelor's in computer engineering from Cedarville. It's a private college in Ohio, but that was pretty cool, and took a tour of the fixed lab, which obviously Dr. Asadi is a part of, back in February of 2020, or sorry, February 2019. That's when I decided, I kind of want to come here when I graduate. So that's where I am now. And right now, like John said, I'm also working in cybersecurity as well. So John is doing a lot with 3D reconstruction. I'm pretty much on the opposite side of that. So once you have your 3D reconstruction, how do you use it to figure out things about PCBs? So think deconstructing this 3D model into various layers of your board, and beyond just X-ray, we're also looking at optical images. So things you take with your regular cameras, terahertz images, and some infrared. So pretty much all across the spectrum. But that's what I'm doing. The picture on the bottom right is me and my lovely wife. Yeah, that's about it.
Excellent. So I'll just start with some of the imaging methods for the terahertz, and then Nathan, if you could describe the infrared FEMOS, I think that would be helpful. So for this, just to show the entire electromagnetic spectrum, all the way from larger radio waves to very, very small gamma rays. In our lab, we currently have multiple tools across the spectrum, such as infrared FEMOS inspection, which is a laser used for interrogating chips non-destructively. And then we have our visible tools, such as optical, microscope, and some DSLR imaging, which Nathan could give a better description of a little later on. And then our ultraviolet and X-ray region, where we use to inspect either the spectroscopy of the molecules, or in the case of X-ray, try and get a volumetric representation of a device from 2D X-ray collection, and then reconstruct that into a 3D volume that can be used for actual verification. So just going to start with the terahertz spectrum, and terahertz is a more advancing region of research for non-destructive analysis. It's currently used for analyzing layers of paint in automotive, or non-destructive carbon fiber analysis, as it's able to penetrate plastics and some other materials that get blocked with optical or typical infrared. So these terahertz methods are very high resolution due to the high frequency operation and that penetration power. However, it's a larger wavelength, so the resolution of this terahertz is very impacted by diffraction from objects that are very small. So it requires a lot of resolution enhancement to improve that imaging. So that volumetric imaging can be performed just with 1 terahertz pulse in 2 dimension, compared to X-ray, which requires rotating of the object. Terahertz is based upon time domain, so it's able to interrogate the object and determine where was that signal's correlation to actual depth inside of an object. And that's why it makes for really good volumetric analysis and that layer analysis. So some of that layered imaging can be seen here, where the peaks of the terahertz pulse can be measured for, in this case, picoseconds, to represent the actual distance or height of objects inside when you're sending that terahertz pulse through. So for this case, this was a integrated circuit. And as you can see on the right, there's some of that diffraction and noise from the terahertz going through the object. And compared to X-ray imaging, which is only able to obtain the density of objects, terahertz is able to perform high resolution spectroscopy as it receives information about the refractive index or dielectric constant. So a lot more of material property characterization can be performed. So it has some of the benefits of, I guess, energy dispersive spectroscopy, kind of like SEM, and in addition to that volumetric analysis of X-ray. So going up the spectrum, I think Nathan could take over to describe our FEMOS tool.
Yeah, so the way that you can think about FEMOS, it stands for photon emission spectroscopy. And it's a tool that allows us to shine an infrared laser that's like a InGaAs or indium gallium arsenide laser onto a processor or just a microchip while it's operating, and see characteristics about that operation. So the image that I have on the right is the actual setup of the system. You can see the knobs over there are literal microscope lenses for regular viewing to show you what you're looking at. And then that entire setup above it is part of the laser system that actually shines down on the chip and does some stimulation as well as some basically reading of what's going on. And on the left is a typical output of this process. So as your laser is scanning over it, there are ways of doing this actively where you actually shoot energy into the device with the laser. And there are ways of doing this passively where you just kind of use your sensor to scan the emissions off the chip that the chip are producing because it's in activated mode and it's radiating its own energy. So that's the difference between like active and passive imaging. But either way, what you can see are these regions of active transistors where the more active something is, the brighter it shows up as a spot. So the way that you can interpret this image is basically when transistors switch from on to off to on to off, they emit a little bit of infrared energy every single time. So if you can think about it like, this way, transistors that switch on and off a lot over time generate more heat and more infrared radiation than transistors that only switch on and off very, very slowly or infrequently. And so on the image on the left, the brighter these spots are, the faster these transistors are switching, and the lower they are, or sorry, the dimmer they are, the less they're switching. And from this, you can infer which transistors are on and which transistors are off, or like active versus not active when you're doing things on the chip. So for instance, if you're looking at cryptographically secure information, then the transistors that are on are transistors that deal with cryptographically secure information that shouldn't be shared with other pieces of the chip. But we have the ability to see those things that should not be visible to someone outside of the chip. So if you just think about like what this means and how you might interpret this, again, the spots that are brighter are switching more often. And if you have a lot of spots right next to each other and each one is a little bit more dim than the next, I don't know what your guys' background here is at UF, like what classes you're required to take. Does anyone know about digital logic or some VLSI, anything like that? You can either raise your hand or put it in the chat or something like that. I'm just curious what your guys' background is. Okay, yeah, so at least one person has some familiarity with digital logic. What this thing is, you can go to the next slide, John, is a clock divider, which you can think about it that one of the brightest spots is the fastest switching frequency, and then different later stages of that clock divider are slower and slower by half the frequency of the previous stage because it divides the clock. And so you'd expect dots down the line or around this cluster to get dimmer and dimmer as the clock divides. And that's kind of what you see here. And I thought that was a pretty cool illustration of something that we learned in digital logic that you can immediately see with your own eyes, and it's the switching frequency. So if we take this back to like an application, if we track those bright spots while we enter something cryptographically secure like a password, then we can follow that trail of bright spots. And that will tell us where these transistors are accessing things from memory. It's a little bit more complicated than that because you have to track the frequency of the bits that you're putting in. So if you know your chip is operating at like 480 megahertz, and you know your set of input characters is like 101010, then you know that as that bit stream is being fed in, then the switching frequency is related to that. So it's a little bit more complicated, but the bottom line, you can look for these bright spots, see where they happen on the chip, and that tells you which memory cells are involved with password data. So then the fun part happens where you can basically take a high-powered laser similar to the one that we showed before, run it over this area in memory, and either corrupt it and put in whatever you want, or cause the chip to go into an invalid or a reset state, where now you have the control over what's going on in this cryptographically secure area. And that should never have happened, but because we know where in memory to look and how to laze it or to put energy into it, we can actually change what's going on in those cells and modify what's happening there. The other option is you can read those cells. So there's other projects that the lab has done where if you look at the configuration of cell technology within these memory banks, you can actually infer what someone's cryptographic key is or their password is. And that's just one example of how we use infrared to exploit at the hardware level when we look at some of these chips. Hopefully that made sense. If you have any questions, feel free to stop and ask them. But yeah, otherwise I can move on to the digital next.
So I actually have a question.
Yeah, go ahead.
So for the FEMOS thing that you're talking about, tracking specifically when transistors are on or off, can you tell the difference between if it's a MOSFET or a BJT or a diode or even like a passive, like a capacitor? Can you tell the difference between those, or do you have to do, like, can you tell when those are on, or do you have to do a little bit more analysis?
So that's actually a great question. I don't know the answer offhand because this is not a project that I've actively worked on. This is just something that people at the lab do. If you do want to know the answer, I know I can put you in contact with someone who would be able to tell you. But the bottom line is if those transistors have different emission characteristics. So for instance, if the energy criteria of a BJT versus a different kind of FET are noticeably different, you should be able to, in theory, detect that with infrared. I don't know the specs offhand because, like I said, this isn't my project, but in principle, you should be able to. It's more so to I guess clarify, even in simple terms, it's a little more complicated than that, but in simple terms, the spots tell you more about the frequency of these operations. So how fast it's switching more than what's doing the switching, because when you aggregate this data over long time periods, you essentially hone in on a certain flicker frequency, and that's what helps you trace the data more so than what kind of emitter is doing the switching. Hopefully that makes some sense. But yeah, it's a good question. And if you want afterwards, I can give you the contact info of the person in the lab who wrote this paper, and I'm sure he would love to tell you more about it.
Oh, that would be really great. Thank you.
Yeah. All right, John, I guess you can move on if you want. Yeah, so this is kind of, I guess, the boring one because everyone's already familiar with what it looks like to take pictures in visible light. I still think it's kind of cool, but it's probably the one that most of you are familiar with. Toward this end, the lab has two semi-major pieces of equipment. So the first is a Nikon D850. It's a pretty standard consumer camera with about 45 megapixel resolution. And the other is a Leica DVM6 microscope capable of anywhere from like 2 to 2,000 times resolution or something like that, or zoom enhancement. And so with these pieces of equipment, we can take full scale pictures of PCBs like you see on the left, or we can get really, really, really close and see individual cracks and contours on any microscopic transistor, or not transistor, but any microscopic capacitor, you know, the ones that are that you might find on like a phone motherboard that are really small. So we can get both of those senses of scale with the equipment that we have. And I'm not going to go into too much detail about how these pictures are acquired or what they do, because probably most of you are familiar with what a camera is. So instead, I'll talk more about the projects themselves that we're working on. John, if you want to go to the next slide. These are all ones that I've done, so I'm happy to talk about it if you want. But the bottom line is, if you've done anything with like image or signal processing, you might be familiar with terms like morphological processing or kernel filtering and all that other good stuff. And I've basically been working on an application to make that process more transparent. So if you want to detect things on this circuit board, which is our ultimate goal for assurance, then there's multiple algorithms you can do to help you, or you can use to help you do that. And one of the tools that I developed is shown on the left too. As you configure these stages and their parameters, you can see what the successive outputs are that led you to the final shape that you have. Another one is if we're taking pictures in bad lighting and we want to normalize, it's something that's done in the photography industry when you're taking, in general, pictures and you want them to look nice, but it's also helpful for characterizing across illumination environments when you are trying to find things on your PCB. So if you look at the quick example here, we have a color checker on the left part of that pipeline that just gives us a sense of like what colors are supposed to be. We know the values of each of those little squares, and we can see what the actual intensity value is in the image we took. We can see that there's a slight green tint to it, and knowing those exact values gives us the correlation matrix between what true green is and what this green is. And we can take that out of the image with this normalization factor, and that's what's being shown here. So that's one of our projects for normalizing across illumination. And then the other one that I have down here is if you take pictures with illumination from the side, you can tell the difference between things with shadows and things without shadows. And you can use that property to distinguish between what's mounted on this board and has some height versus what's just like a contact pad and shouldn't have height, and I don't care about because it's not a component that's been mounted on the board. And you can see the difference between those things once you shine enough lights on this and look for shadows. And there's more than this, but these are just the most prominent ones that I've worked on recently. But yeah.
So unless you have any questions on that portion for Nathan, I can go on and describe some of the interior internal inspection we do with X-ray. So to complement the optical inspection for the outside of the board, we also need to collect X-rays of the internal components to get the full understanding of how is that board designed and what are the internal connections such as traces and vias. So in the case of an X-ray scan, the board rotates on our rotation stage here, which is an air bearing. So it's very stable, so there's not a lot of movement as the sample rotates. And on the right, we have a X-ray source, which is a micro CT source. And the X-rays are collected on the flat panel you see on the left. And in some cases where we need higher resolution for small field of view, we can use this CCD camera. However, the benefits of the flat panel is you can image large field of view very fast. So the CCD camera is typically used for imaging like a small region on a board or a specific chip. So the importance of all of this X-ray collection and analysis is to verify that internal circuitry. So as you see here on the bottom right, there's an example of a cloned printed circuit board. So the design was reverse engineered and then duplicated and was being sold on the market just as if it was a real printed circuit board. So sometimes it's actually difficult to know whether the board that you're buying on the market is valid or not, or is actually designed to the specification that you had ordered. So in some cases, you'll need to do verification of a few of your printed circuit boards, but for high volume inspection, you really need to have an understanding of the X-ray process to speed up that inspection so that you are not spending hours for analysis of a board if it only requires about 30 minutes. So we're trying to work in the lab on determining ways to simulate X-ray collection of printed circuit boards so we can provide a more algorithmic way to determine the X-ray parameters, and in addition to the geometries for collection. So as you see here, the traditional rotation is the computed tomography portion of X-ray collection, and there are some issues constructing these two-dimensional projections you see on the left into a 3D volume accurately. And a large portion of this is the poor collection information from 90 degrees and to 270 degrees, where almost no information from the inside of the board is actually collected. So this really messes with the reconstruction algorithms. So this is known as the limited angle problem, because you only have information from limited angles about your object. So we're trying to work on optimizing what are the best angles to collect from the board, and then creating and tuning algorithms for reconstruction for electronics. Right now, there's a lot of work in the medical domain to improve reconstruction for healthcare and clinical CAT scans and MRI. However, for electronics, there's not a lot of work into these reconstruction algorithms because X-raying of printed circuit boards is a newer research field. So we're definitely trying to look into how to optimize the collection and then that reconstruction process. And after the data collection and then the reconstruction, that's what gives us the 3D volume. So from our 3D volume, some of the work that our other students in the lab, including Nathan, have been working on is creating interfaces and automated methods for users or to create algorithms that can go through the 3D volume and either provide verification by checking the design. So similar to optical, just checking if that component is supposed to be there or not. We can do the similar things for the internal layer of the board. So that all begins with aligning the collection of the 3D volume. So that's the first step for making sure that your data is all going to be in the same plane. Otherwise, you'll get some stitching errors and you'll get some slice errors as you're trying to make sure that the components of the board are all actually connected. And then after the alignment, that's where we go on to the segmentation. So this takes all of the features of the board and tries to figure out what is their actual functionality and their connectivity between each other. And that's a combination of some edge detection and region growing. And in some cases where the high resolution scan is possible, this can be performed automatically. However, in some cases where the board has a little bit more noise due to metallic parts or issues during that reconstruction process, it might require annotation from a skilled expert to figure out where is that component actually end. And then from that annotated or the segmented volume, we can create this DXF drawing, which just tells us it's like a vectorized format of the board's layout in each layer. And then from there, we're still working on developing that connectivity, so that continuity connection, and then the classification of the components to perform this automatically. And as you see here, this Gerber, drill, and netlist files these are the manufacturing files or the blueprints of a printed circuit board. So the end goal is to be able to take a 3D volume and input it into the software that we're developing and be exported with the design files so that we could provide a dimensional check of, do all the components connect how they should, and are they the actual sizes and conductivity, and do they have the proper resistivity to make sure that the functionality of the board would actually operate as it was intended to. So going on to some other methods that don't involve the actual collection of photons, we have the electromagnetic based other techniques such as SEM or FIB, which is the scanning electron microscope, or focused ion beam. So often you'll see SEM and FIB combined together because SEM is used for collecting electrons from the surface to actually provide very, very high resolution imaging. If you're not familiar with SEM, but FIB is used to mill away some of the surface material that might be there, or in addition, you can actually deposit material in that place. So just showing here, here's an example of that deposition, and some material has been deposited in the shape of a familiar object. And on the left, this is an example of removing of some material that might have been blocking some sensitive circuitry. And then this is an actual SEM image. So that's why SEM and FIB go together very well for inspection. So to get higher resolution than SEM, we have the tool, which is called the NanoFab. And the benefits of this is you're able to get atomic level resolution. And there's some very fancy, impressive optics, alignment, and techniques that are necessary to actually get that tool's resolution for the stability and calibration. So I'm not actually so familiar with how the data is collected at the atomic scale. If you have any questions, we could discuss that at the end. But to go on to some of the other techniques, and this is SAM. So this is our surface acoustic, I'm missing the M, but it's a scanning
acoustic microscopy. So
microscopy.
It's right. So it's like if you could use vibrations to take pictures of what you're and measure what those vibrations look like. You can plot those, and if you plot them in a 2D pattern, you can see what the chip looks like. An example of that shown here.
Yes, perfect. And just another example, you want to continue for the near field raster probe.
Right. So there's a bunch of different things you could do. So another one is if you take a sampling of the electric field around a chip as it's operating over multiple different points, you can plot the intensity of change or the phase or whatever you want of different things going on that chip. So what some people have been able to do is what's called side channel attack. So the photon microscopy one that I talked about earlier is one example. This is using either the electric field or the magnetic field or whatever different, I guess those would be the most common ones to probe. And based on their values, you can figure out what's changing or what's going on inside the chip. And so that's not really using photons, but that is a different way of measuring intensities, like I said, either voltage or maybe current or just looking at what those field values are around your chip and plotting what they are. And in some cases, I can tell you where activity is going on the chip, what that activity is if you're lucky enough, or especially for RF equipment. So like if you're trying to figure out the radiation patterns of antenna, something like this is really commonly done.
And would you have any comments that I missed for the NanoFab for the inspection there at the atomic level?
Oh, not so much. The NanoFab is basically a very expensive version of the SEMFib, where one of the coolest things I saw about it is for the alignment. Basically, you have 3 atoms in a triangular pattern, and a single atom can fit on the space in between them. So if you look at sphere packing, if you have a configuration of 3 spheres, you can fit 1 sphere underneath of it, and they literally use that for calibration of this machine at a single atom level. And if you're looking at the pictures from this device, depending on how it's been calibrated, you can see the actual like valence orbitals of different configurations of silicon atoms. And it's really fascinating to see it with your own eyes.
Yes, it's quite, I think it's the most expensive tool that we have.
Yeah.
And just a more in-depth description of that SEM fib, some of the operation there. So the tools that we have 2 SEMs, and we use them quite often. And just to, instead of those photons interacting with the surface, we're actually scanning across the surface and collecting the electrons. So that's where the scanning electron microscopy comes into play. And some SEM tools have more capabilities than others. So that might be an array of different sensors from different angles. And what you can do with that is you can do a lot of topological analysis, such as collecting the different backscattered electrons and secondary electrons from different angles. and you can get some very interesting topological analysis just by looking at from the X or the Y of a certain region to really understand, okay, it was maybe scratched in this way, or I'm seeing something different from the backscatter at one angle compared to another angle might tell you a lot about what's actually going on inside the sample. So continuing on to the nanofab, it's just like Nathan had said, the much more expensive version of this and higher resolution, and that gives you that atomic level inspection. So going on to show the actual operation of these different points. So this looks very similar to the FEMOS tool, where there's regions of bright intensity. So similarly, the electrons are sensitive to different areas, such as the areas of high diffusion, such as these contacts, or different polysilicon features, such as these lines that provide the connectivity. So using these SEM images, this is how you're able to scan across the surface and collect the electrons from all the different regions. And this is typically done in little like grid patterns, and then it's actually all stitched together, and that's the full SEM image that we're actually seeing. So this process is, it's not extremely damaging to the sample, but it does impose a slight amount of charging to the sample. So if you're collecting very, very high powered SEM images, you're going to maybe see a burn spot on that region of the chip. So in terms of reverse engineering or attacks that someone might do to your chip, you can actually detect if this has been performed by checking for these burn spots. And some of these burn spots are actually used for verification of the chip as it's being used as it's being manufactured. They often collect SEM images to verify that the process steps are going correctly. So that's why a lot of the tools in our lab are based upon failure analysis and other inspections used in industry. And sometimes these attackers, or for verification, those same tools that are used to make sure that manufacturing is going along smoothly are also used for reverse engineering or attacks, such as that case of the FEMOS, where just a laser is able to see the operation of the chip. So going on to describe the fib portion. So if you have some material that's blocking your die that you want to interrogate, you'll often go in and polish or remove a lot of this material with more mechanical methods, because if you tried to do this with fib, it would take a very, very long time. Fib is very effective at small areas and areas that you know a lot about the composition. So you can actually tune the ion that you want to shoot at the surface, and certain ions are able to remove more material at a faster rate than others. So for silicon, gallium is often used, and some other materials, they shoot different ions to actually cause a stronger interaction to remove more of the material. And as you can see, you can create these micro pillars, which are often used for verification. They'll take this micro pillar and go use this for TEM imaging, which we don't have a TEM in the lab, but TEM is the very, very high resolution imaging with electrons. However, instead of capturing the reflection, you actually shoot electrons through the sample. So the sample needs a lot of preparation to make it thin enough that electrons can actually go through it. So that's where these micro pillars actually come into play. Or in other instances, you might want to interrogate a chip from the cross section to verify some functionality. In this case, this looks like a source or a drain region that they're trying to verify. So I will hand it over to Nathan, how much time we have for discussing the grad school experience. And Nathan, just let me know when to go through the slides and such, but I know we're at like going over 30 minutes here, but I think we can probably spend another 5 minutes on this and then some questions.
Yeah.
That sounds good.
So yeah, this is basically if any of you are interested in what it would be like to go to grad school after you get your degree, I know that I had some ideas of what it looked like, and what I've experienced, at least at the Fix Lab, has been different from some of those experiences or some of those preconceptions about what it might be. And we're just going to talk a little bit about that if that was of interest to people in some of the remaining time. I guess before I start this, does anyone have questions on the technical portion? I think that your class like ends at what, 10 till, so we have about 10 minutes left to go through some of this. In the absence of response, I guess we can just go forward with it. But yeah, so when I got my degree, and I guess in the last semester leading up to it, I was trying to figure out what to do about whether I get a job, whether I go for a master's, whether I go for a PhD. And I didn't really have a lot of resources to go to at my school. So a lot of this was unknown to me, like whether I might have to pay for a degree or what the difficulty would look like, what the time involvements would look like. So, and I've heard multiple different things. Depending on who you ask, you might get different answers, especially depending on if they're like not doing an engineering degree. So if you know anyone that's doing like a medical degree or like a bachelor's in or they're getting an advanced degree in arts or history or something like that, it will cost, it more than likely cost some money to go there. For engineering, you literally get paid to get your degree. So John and I are here. We get free tuition. We also get a stipend. We have vacation days. It's kind of like a job in that respect. It's not much, but it's enough to live off of while you're getting literally a free education. So it will not cost you. It'll only benefit you financially, at least in the long run. It does take a few years to get there, but it's not something that you have to budget for out of pocket at the moment. Another thing that I've heard and that people have experienced is that it's much harder than undergrad. In my opinion, I like project-based work a lot more than having homeworks due every 3 to 5 days with a syllabus full of a bunch of assignments and taking 6 courses at once and all that other stuff. In grad school, the project-based aspect is a lot more prominent and popular. So in general, you take 1 to 2 courses at most over the year or over the semester. So you have a lot more time to focus on your research. Almost all of your objectives and your requirements are not based on a syllabus, they're based on general research goals that you pursue. So if you're not self-motivated, it can be a little difficult, but for me, it was a lot easier than undergrad. I don't know if John had a different experience, but that's been the case for me coming from my undergrad to grad school here. And another popular one is that you might, like another popular myth is that you might not have much creative freedom to do what you want on a project basis or on a research basis. And some professors are limited by funding, so they can only fund you to do specific research tasks and specific goals that align with their grant proposals and what they're allowed to pay you for. At least at Fix, that umbrella is very large. So the sponsors of the lab, pretty much anything that has to do with hardware security and cybersecurity. So if you have this brand new idea that we don't know anything about, but you can show that it can be useful for hardware assurance, then the professors are happy to let you explore that. So you have 2 of the projects that I'm on, I got to basically invent. It's not like they were done before. It's just, but we showed that they have legitimate impacts in the realm of hardware security. And so we were free to pursue them ourselves. And again, that's something that will probably be different depending on where you go, but at least at Fix, you do have a lot of creative freedom to manage your own projects. And John, I don't know if you want to chime in and counter or add to any of those points, but those are the most common ones that I've heard of, at least when I was looking at grad school experiences.
Yes, I definitely agree on the undergrad, where it's not just an extension of undergrad. It really is, you feel like you're working on your own research and you're building your own knowledge, and you get to choose what classes you would like as well. So you have a lot of like that combined creative freedom, and it's definitely something different than undergrad. While you might not get this creative freedom opportunity in industry, you might get there after building your credibility for a little while, but in terms of being able to work right on the things that you're interested in, that's something I can speak for at Fix. I know other students here at UF in the EC department, they also enjoy what they do in some of the other labs. So I think that goes across the board. yeah, if anybody had any questions on these, I think before we would move on.
I guess while we're waiting, you can hop to the next slide. There's a small graphic that just shows financially, yes, you are not making as much as some of your peers that have got their degrees and start working in industry right away. In fact, you'll be making about half or less of what they make right as you start. But when you finish your PhD, pretty much the sky's the limit financially, if that's a concern. You immediately start with a higher wage in general. You have a lot more promotion opportunities, and your career pathways are also drastically improved, especially now. Like, technology is way more popular now than it has been in recent years. And like, it's been popular before. So the demand is incredible. And for better or worse, a lot of those are US citizen based jobs. So like there's plenty of jobs for everyone that's interested in tech, but specifically there's a lack of US citizen PhD students and people interested in getting their graduate degrees here. So that extra demand has made the benefits of getting a degree even better, at least for US citizens if you're interested. So this is just a quick graphic that shows after you finish your PhD and enter industry, over time, you end up like the area under the curve, if you were to take an integration of these different salary points, is in favor of getting a PhD after just a few years, if that was a concern.
And then similarly, when I was in my undergrad at materials, I had one of our professors who had just joined. He was one of the newer professors, but he showed us a similar graphic, and he wanted to emphasize the importance that if you want some more creative freedom and on what you're going to work on later in life, that the doctorate's there, but he also tried to get us with the financial side of it as well. And then Nathan's points on saying that you don't have to pay for grad school. It's really something that you're paid to do, and it's like you're an employee, less than something that you're shelling out of pocket for. I guess I could go on to just some other key points.
Yeah, these are just kind of a collection of topics that I thought would have been nice tidbits to know as I'm looking. And one of the biggest takeaways by far for me is it doesn't matter what you're doing. If you go to engineering grad school, whether you're doing electrical engineering, computer engineering, your computer science, whether you're looking at code or materials or whatever, everyone is using machine learning. So if you wanted to get a head start on what that would look like and dabble in some of these classes, and especially what it'd be like to implement some of these machine learning algorithms in code, it will only help you. No matter what you do, almost everyone will want to know about your ability to handle data sets, to separate them into different classes and clustering them and all that other stuff. But machine learning is a huge buzzword right now. So if there's anything that you take away from thinking about prepping for grad school material-wise, I would recommend machine learning. You can't go wrong. And just the last slide here is about personal reflection of once you are here, what does it really look like? What are the biggest differences between like now and what you might have experienced in undergrad? For me, learning to say no was important. So in undergrad, you have a syllabus, you're given almost everything from day one, and you can choose to work ahead and just like get it all wrapped up. And then you don't have any work to do afterwards if you don't want to. At least that was the way a lot of my classes operated. In grad school, that's not really the case. So like John and I have been saying, it's very project-based. So and those projects don't really have clear defined goals and outlines because it's your opportunity to research and make something of the field. And because of that, if you just meet your objectives, the only thing waiting for you is more objectives, which in some ways is really cool because it means that you can progress at your own speed. You have a lot of opportunities to do different things, but it also means if you don't know how to say no and if you don't know where your limits are, you can end up overworking yourself very quickly. And there's it's well known that the mental state of a lot of grad students is often not good, and there's a lot of burnout. And this is part of the reason why, is because people don't really know how to pace themselves on their projects. It's not like a syllabus where you get you have a set amount of work over the semester and then you're done. At least in many cases. Some places are different, but here anyway, that's kind of the case. And the other important takeaway for me as I was reflecting is to kind of when you're doing your work, look for the problem before you start finding the solution. So in a lot of textbooks, they'll tell you about a theorem and the proof behind it. And then right after that, there's a list of exercises, and it says, and based on the exercises and the fact that you've just learned the solutions, you know what to apply where. In grad school, it's kind of the other way around. So you don't know the solution ahead of time. All you know is there's a set of problems that you're facing. And if you try to address it with the textbook example of learning a solution and then trying to find problems that relate to it, you're going to be looking for a while without too many results, because that's not generally the way that new research is developed. You take a look at the problem, you sit on it for a while, and you experiment with different solutions as you go. But yeah, that's about it. That's all the material that we had to go over, and we're happy to elaborate on anything. I know it's right at the class time, but if anyone wanted to stick around and ask questions, that's totally fine too. And John, I think you can stop the recording if you want.
Okay.
All right.
Click it. All right.